Today we are going to do some exercises from oscillations and waves. Oscillations and waves. First of all, we will do exercise number 3. Exercise number 3 from oscillations and waves. Oscillations and waves. A small body with mass m is fixed in the middle of the string of length 2L. The tension of the string in the equilibrium position is equal to T0. This is the tension of the string in the equilibrium position. Find angular frequency of small perpendicular to the string oscillations of the body if the mass of the string is negligible and there is no gravity. Maybe I will try to draw a picture. That will help us to understand what is necessary to do. I'll draw equilibrium position with dash line. This is the equilibrium position. Equilibrium position. And here in the middle of the string, we have a small body. That is fixed in the middle of the string. And here we have this string. The oscillations are up and down. This body moves up and down. So we can use vertical axis to describe the motion of the body. We can use vertical axis. X. Here we have 0. And according to the condition, this is L, and here here we have double L. Double L. Here we have double L, and here this distance is x. This is x. Okay. So do you have any ideas? Do you have any ideas how to what to do? What to do in this situation? We have to find angular frequency. Angular frequency or natural frequency of small oscillations of this mass on the string. Okay. I think we can remember differential equation of small free undamped oscillations. Differential equation of small free undamped oscillations. It can be written in this way. Second derivative of x plus omega 0 to the power of 2 x, and this is equal to 0. This is equal to 0, and this is natural angular frequency or natural circular frequency. So if we build this differential equation for this string, we will be able to find this angular frequency. Okay, do you have any ideas how to build this differential equation? How to build such differential equation? Such differential equation for this system that is shown on the picture. No ideas. No ideas. Okay, I think we can use but first of all, what is necessary to do? When we are solving dynamics problem. The first step that is necessary to do when we are solving any dynamics problem. What is the first step? Maybe someone can remember. It is from our lessons that we had in September and October. The first step to solve any dynamics problem. The first step is to define forces that act in the system. Forces. So what about forces? What about forces? Can you define any forces? Any forces in this system? No. Okay. Mm. According to the condition, uh, we have the only one force. The only one force is this is tension of the string, or force of tension, or force of tension. Force of tension. It can be shown in this way. It can be shown in this way. So here we have T1, T2. We have to use different signations because these are different vectors, but they have the same absolute values. So we can write absolute value of the first vector is equal to the absolute value of the second vector, and this is equal to some t. Okay, so this is force of tension in the string, and according to the condition, there is no gravity. And if there is no gravity, so can the next step is to define is to find this. This is the next step. And how to do this? Okay. I understand, but it is necessary not to confuse this. In this case, it is not a period, it is not time, it is force. So it is not time. it's a pity that we have the same signations for force of tension and period of oscillations. But these are completely different values. Completely different values. So I think we can use Hooke's law. We can use Hooke's law, and according to this law, we can assume that in equilibrium position and in equilibrium position that we have T0 is K multiplied by 2L, where K is a spring constant. K is a spring constant. So we can find this spring constant. We can find this spring constant. K is equal to T0 divided by 2L, where K is spring constant. And this spring constant we can use to find T. We can use to find T. But we need this. In this case, we need this length. So can we find this length? Can we find this length? This length. From the picture. Yes, okay. Okay, so we have half of the string length in position X. In position X. Okay, that's right. That's right. That's right. I agree with. I agree with you in this situation. So we have that in this position. In this position is square root of x to the power of 2 plus L to the power of 2. So according to this, we have that T is equal to k multiplied by 2 square root plus L to the power of 2. And according to this, we have that this is 0 square root x to the power of 2 plus L to the power of 2 divided by 2L, and this will be equal to T0 square root x to the power of 2 plus L to the power of 2 divided by L. Okay, so this is a force of tension. This is force of tension. In this case, maybe I will clean something from the picture. To improve it. Now I will return that we need here. So according to the picture, here we have T2 and here we have dash line and here we have square root plus L to the power of 2. Okay. So we have defined forces. In our system, and can we build differential equation? And how to do this? Okay, maybe you can remember. The second Newton's law. We will use second Newton's law to build differential equation. But I will write this in projections on the direction of the motion. I will write this without vectors. I will write this in projections. Okay, so what can you say about acceleration? About acceleration, how to write this? How to write acceleration? We need the definition. We need the definition of acceleration. We need the definition of acceleration to from kinematics to build the differential equation. We have to act in the same way as we did yesterday, and as we did on Wednesday, last week. The definition of acceleration from kinematics. Oh, yes, this is that's right. That's right. This is definitely what we need in this case. Okay. Okay. So and what about F? What about F? No, we cannot do this. We cannot do this. We cannot do this. What we need, I'll show this force on the picture. This is projection. This is projection of force on x-axis. This is projection of force on x-axis. So I'll draw this. So F, force F is here. Force F is here. This is force F. So can we find this force from the picture? This is projection of forces T1 and T2 on vertical axis. Okay, maybe we can draw another picture. So if we have, for example, if we have two forces. If we have two forces, we have this situation. Here alpha, this is T2, this is F X, and this F, this is F Y. Okay, so how to find fx? How to find fx from this picture? Sine alpha. But in this case, it will be tangent. Yes, this may be, but for this formula, we have to know Fy projection. But we don't know Fy. We don't know this, so we cannot use this formula because we don't know this. Maybe we can use this angle alpha. So fx is equal to the modulus of T2 multiplied by sinus of alpha. Multiplied by sinus of alpha. So this is T multiplied by sinus of alpha. Sinus of alpha. So is it clear, or maybe you have some questions? Okay. So we have in this case fx is equal to T sinus alpha. So from here we have this triangle. But from here we have almost the same situation. We have that fx is equal to the modulus of no T2, T1, T1 sinus alpha, and this is also equal to T sinus alpha. T sinus alpha. And so we have that f is equal to fx, and this is equal to 2t sinus alpha. Okay, so do you have any questions? Do you have any questions? Okay. Okay. So let's continue. Let's continue. In this case, so let's continue. Let's continue. What we need next? We need sinus alpha. Sinus alpha. Can you define sinus alpha? Sinus alpha from the picture. Alpha is here, of course. Alpha, and here we also have alpha. Yes, this is equal to x divided by square root of x to the power of 2 plus L to the power of 2. Okay, that's right. That's right. So we have found vertical projection of the force. So we can use this here and this here. So from this we have 2 T0 square root fx to the power of 2 plus L to the power of 2 divided by L multiplied by x divided by square root of x to the power of 2 plus L to the power of 2 plus L to the power of 2. And this is equal to 2T0 divided by L multiplied by x. Okay, this is what we need in this case. Okay, so we can use the second Newton's law the second Newton's law in our situation. So this will be m multiplied by d2x divided by dt 2 plus this will be this will not will be in this case. I have forgotten to write minus. This will be minus here. Will be minus because of the direction. Because of the direction. This will be minus here because of the direction of the force. Because of the direction. Because the x is from down to up, and the force F is from up to down. So this will be minus 2t0 divided by L multiplied by x. So this will be d2x divided by dt to the power of 2 plus 2 multiplied by t0 ml multiplied by x is equal to 0. Okay, so this is our differential equation. So do you have any questions? Do you have any questions? No questions. Okay, if there is no questions, I will clean some unnecessary information from the screen. Clean some unnecessary information from the screen. So we have got differential equation of three small undamped oscillations. And we can compare this with general form of this equation. We can compare these two equations. We can compare them. And from here we can make a conclusion that this is equal to natural angular frequency. So from here we have that omega 0 is equal to square root of 2t0 divided by ml. divided by ml. Okay, do you have any questions about this? Do you have any questions? No questions. Oh, this is the answer. This is the answer for this exercise. Okay, the next exercise is number 4. The next exercise is number 4. Exercise is number 4. The next exercise is number 4. Exercise number 4. Two physical pendulums make small oscillations around the same horizontal axis with frequencies respectively omega 1, omega 1, omega 2. Omega 1 and omega 2. The moments of inertia related to this axis are respectively equal to I1 and I2. I1 and I2. The pendulums were set in stable equilibrium and fixed to each other. What will be the frequency of small oscillations of the pendulum that was created after fixing? Maybe I will try to draw for example, the first pendulum. Equilibrium position will be shown in dash. It will be shown with dash line. This is the equilibrium position. And this is some physical pendulum. With, for example, mass m. So we have vertical force m1g. Here we have some distance r1 angle phi and angle phi. Okay, physical pendulum. So can you remember for example, natural circular frequency of physical pendulum? Okay, okay, that's right. That's right. This is definitely what we need. So we can use this, for example, for these two frequencies. So we have that omega 1 is equal to square root of m1 g r1 divided by I1. So from here we can write that omega 1 to the power of 2 is equal to m1 g r1 divided by I1 So this is first circular frequency, and for second we have similar formula m2 g r2 divided by I2. Okay, so what do we need? To use this? What do we need? We still need we need to know m, for example. We need to know r, and we need to know the moment of inertia. So how to define them? How to find them? It is necessary to remember that we have pendulum that was created from two bodies, two pendulums with masses m1 and m2. So we have the big pendulum that was made of two small ones. So according to the condition, we have that m is equal to m1 plus m2. Okay, and what about the moment of inertia? What about the moment of inertia? Moment of inertia is also an additive value. Situation is similar to the situation with mass. So moment of inertia is also an additive value. And the axis of rotation wasn't changed. So axis of rotation is the same. And according to this, we can write that this is I1 plus I2. Okay, okay, and what about R? What about R? Oh, it's a pity, but it is not so simple in this case. It is not so simple. I think we need something. Okay, it is not so simple. It is not so simple in this case. I think it will be distance. It will be distance between the axis of rotation and the center of mass of a big pendulum created of two small ones. So we need the center of mass. We need the center of mass. We need to remember from our lessons in September and October. We need to remember how to find the center of mass. How to find the center of mass. But maybe I'll remind the formula. Radius vector of the center of mass is equal to the sum of mi ri divided by the sum of mi. It is from one of our previous lessons from September or October. So we have to use this. And in this case, we have M1 R1 plus M2 and R2 divided by M1 plus M2. Divided by M1 plus M2. Okay, so do you have any questions? No questions. Okay, so now we can use this formula. But I will make some changes on the screen. I will move this. And maybe it is necessary to write this here. So M is equal to this R of the center of mass is here. Okay, so we can write that this is equal to this is equal to square root. It will be square root of m1 r1 plus m2 r2 r2 multiplied by g divided by I1 plus I2. Okay, and we can find from here that m1 r1 is equal to omega 1 to the power of 2 multiplied by I1 divided by g, and m2 r2 is equal to divided by g. We can use this here. And from here we have that it will be omega 1 to the power of 2 I1 plus omega 2 to the power of 2 I2 divided by I1 plus I2 square root. Okay. Do you have any questions about this? Well, this is the answer. This is the answer. This is the answer. Okay. So the next exercise is number 5. Exercise number 5. Exercise number 5. Exercise number 5. A homogeneous rod of length L, makes small oscillations around a horizontal axis O1 that is perpendicular to the rod and passes through one of its points. Find the distance between the center of mass of the rod and the axis O1 if the period of oscillations is minimal. If the period of oscillations is minimal. What is the value of this minimal period? So I'll draw a picture that will help us to understand the situation, the equilibrium position will be traditionally shown with the dash line, equilibrium position. And homogeneous rod. Homogeneous rod. It is something like this. A homogeneous rod the axis O01 is perpendicular to the screen and passes through this point. Axis of rotation O01 is perpendicular to the screen and passes through this point of intersection between the rod and dash line. This is angle of rotation. This is the angle of rotation. Somewhere here we have gravity force. mg. Somewhere here we have gravity force, and here we have the distance between axis of rotation and the center of mass. And the length of the rod is L according to the condition. The length of the rod is L. Okay, so what can you say about the period of oscillations of this system? What can you say about the period of oscillations? I think this rod, this system, is a case of physical pendulum. We have case of physical pendulum. So according to this, we can write that omega 0 is equal to square root of m g r divided by I square root. Okay, and what about the period of small oscillations? What about period of oscillations? Yes, okay. Okay. Okay, that's right. Okay, that's right. That's right. So we can we have the formula for period. Okay, but we need to find its minimal value according to the condition. We need to find its minimal value. We need to find its minimal value. How to do this? How to find minimal value of the period? Okay, this value t will be minimal when the expression under the square root is minimal. So to minimize this, we have to find minimal value of this. Because the square root increases with increasing of its argument, so we have to find minimal value of the expression under the square root. Okay, how to do this? Maybe first of all we need to find explicit form of this expression. Explicit form. I mean that we need to find the moment of inertia as function of r. So we need to find the moment of inertia. We need to find the moment of inertia. So we need to remember something from our lessons that were in September and October. We need to remember something from mechanics. Something from mechanics to find the answer. I think maybe we can use Huygens-Steiner theorem or parallel axis theorem. We can use parallel axis theorem. According to this theorem, this will be I0 plus m r to the power of 2. M out r to the power of 2. Okay, and what about I0? What about I0? What about I0? Can we find this? Can we find this? For the homogeneous rod. maybe you can remember from mechanics that the moment of inertia of a homogeneous rod in relation to the axis that passes through its center of mass and perpendicular to the rod is equal to m L to the power of 2 divided by 12. Is from mechanics. So we have that that this is equal to m L to the power of 2 divided by 12 plus mr to the power of 2, and this is this is m L to the power of 2 plus 12 r to the power of 2 divided by 12 divided by 12 divided by 12 divided by 12. Okay. Okay, so we can use this here. We can use this here. Let's do this. Let's do this. Let's do this. This will be 2p 2p L plus 12 r to the power of 2 divided by 12 g r. Well, gr. Okay, we have just written the dependence of period on r in explicit form. So we can find its minimal value. How to find minimal value of the period from this formula? We need to remember calculus. According to calculus, the function is minimal when its first derivative is equal to 0. When its first derivative is equal to 0. So to find the minimal value of the period, we have to find minimal value of the expression in square root. So we have to find derivative of this expression plus 12 r divided by 12 g r. Okay. Okay, let's do this. or maybe you can find this derivative. But why? I cannot understand this. I cannot understand. I cannot understand this. I think we can use formula for derivative of this expression. D by dx, for example, of u divided by v. This will be d by dx v minus dv by dx. We can use this formula from calculus. We can use this formula from calculus. No, this was good. This was good. Sorry, but a derivative of L to the power of 2 is equal to 0. L is constant. L is constant. So maybe I will continue. I will continue this by myself. So we have that this will be 24 r multiplied by 12 g r minus L to the power of 2 plus 12 r to the power of 2 and 12 g. and divided by 12 g r to the power of 2. And so according to this we have that this will be 24 r to the power of 2 minus L to the power of 2 plus 12 r to the power of 2. R to the power of 2. R to the power of 2 and divided by r to the power of 2 12 g. Yes, and this is equal to this is equal to 12 r to the power of 2 minus L to the power of 2 divided by 12 g r to the power of 2. LGR to the power of 2. Okay, and this is equal to 0. This is equal to 0. Okay, maybe I will clean some information from the screen. I will clean some information. So we have found this derivative. And according to this we can find from here that r should be equal to plus or minus L divided by square root of 12. But the distance is always positive. The distance is always positive or non-negative. Distance is always non-negative, so we have to choose plus. We have to choose a positive. So, and this is square root of 4 multiplied by 3, and this is L. And this is okay. So this is the distance when the period is minimal. Okay, and let's find minimal value of the period. This will be this will be 2p square root L to the power of 2, L to the power of 2 plus L to the power of 2 divided by 12g L divided by 6, and it will be 2p 2p square root L divided by square root of 3 g. It will be this, and it can be written as 2p square root of 3l 3g. Okay, do you have any questions about this?
No, teacher.
No. Okay, in this case, the last homework, it is from oscillations and waves. This will be our last homework. This is number 1. Number one from oscillations and waves. Number 1 from oscillations.
Okay, teacher.
Okay. Okay, so thank you for your attention. I hope to see you next week.